So let's see. So the current set, which is extra credit is due today. There is another assignment that will be posted later this afternoon that will be due in 1 week. And the final project, I'll be discussing that soon. We have a few more assignments. We'll get to discuss that very soon. All righty. So, last time, God, what the heck is that word? We quantized the electromagnetic field. And the way we did it was just to decompose the field into the normal modes, but those normal modes have to satisfy Maxwell's equations, okay? And so any normal modes that satisfy Maxwell's equations are good. And in particular, we're looking at the quantization of what's called the free field, right, in the absence of charges. Okay, so this is the field itself, not the interacting field. Okay, come back to that story. And the free field, thus a very nice set of normal modes are plane waves. Okay, we have a set of electric fields that are plane waves, and similarly for the magnetic field, there are a set of normal modes that are plane waves, but the E and B field, the mode, the electric field and the magnetic field associated with those modes are not independent of each other. They're constrained by Maxwell's equations. Both the fields have to be divergenceless, and that is satisfied if this vector is in the plane transverse to the k vector. And so both of these satisfy del dot E and del dot B are 0. And moreover, E and B are related to one another through the Faraday law and the Ampere law in free space. Okay, Ampere Maxwell law. And these are plane wave solutions that do that. Okay, that we've all learned about. The normal modes are specified by an oscillation frequency, and that's determined by the dispersion relation, okay, which comes out of Maxwell's equations. And so the modes themselves are orthonormal with respect to the different indices that specify the modes. The modes are specified by the wave vector and by the polarization. There are two orthogonal polarizations that form a basis of possible polarizations. We can choose whatever basis we like here for reasons that we'll remind ourselves of. I'm choosing that basis to be right and left circularly polarized polarization, which correspond to what we call positive and negative helicity. Okay, and so the modes are orthogonal. Again, we're looking at things in a quantization volume. So we've created a box that has some length in x, y, and z, Lx, Ly, Lz, with periodic boundary conditions. It's kind of a torus, three-dimensional torus embedded in a four-dimensional imagination. And that quantization volume at the moment is there for convenience. It's a way of discretizing the modes, but in practice, we might be considering a true volume, like we have a superconducting cavity where we have microwaves, and like we do, or they do in, you know, the chips, we'll get to one moment, Nate. We have, you know, modes of a microwave cavity that are, I'll say, used in coupled to superconducting transmons in superconducting quantum information processing, and the modes there are determined by the physical boundary conditions. Yeah, Nate, you had a question.
Does that
Normality.
relationship apply to both E and B?
Yeah, I mean, so they do. So since this is true, it will also be true that these will be orthogonal once you take those dot products, assuming this relation. It's one and the same relation. Okay? But yes. Okay, so once we have the modes, then we just write down the quantized field. Ta-da! Here it is. So the quantized field is basically a quantum version of the Fourier decomposition of the field decomposed in terms of the normal modes. So this is really just a Fourier decomposition, okay? The Fourier amplitudes thus become the creation and annihilation operators. And for historic reasons, this is called the positive frequency component, and this is called the negative component. Yeah?
By convention, we always have the omegas be positive and we tack a sign on outside of them as needed.
Yeah, this is good convention. The thing that goes like either the minus I omega t is called the positive frequency component because things go like that, and that's where the positive get plus is the constant of that. So that's Roy Glauber, who is kind of the godfather of quantum optics, called them that, and we always do for that reason. Okay? And similarly for the magnetic field. You know, I should note the electric and magnetic fields don't commute with one another, which is interesting. So there's a kind of uncertainty, but you can't simultaneously. There is no state of the field that has a well-defined electric field where there's quantum uncertainty. We'll talk a lot more about that. That's kind of interesting. Just like position and momentum don't commute with one another. Yeah?
So if the E and B field don't commute with each other, then when we originally created our, for example, our momentum where we have E cross B classically, and then we just turn them into operators, how do we know what orientation we have to have them?
Yeah, that's a good question. At the end of the day, if we have things like E and B in a certain order for like the momentum vector, we have to ask whether that is a Hermitian operator or not, okay? If it's a Hermitian operator, at the end of the day, doesn't really matter, we can symmetrize. In that case, that cross product is actually independent of the order. But we'd have to think quite carefully about that, about operator order. Yeah?
Are they generators of each other?
Sorry?
Are they kind of like, for instance, like if I want a displacement, I need some momentum. I need some momentum to generate a displacement. Does it work with this too? Like if I want a magnetic field, I need some electric field to generate it.
Well, okay, so we'll talk a lot more about generators soon. The thing that generates fields are currents. So currents radiate fields. The currents are the generators of the field. So we'll get to that. Maybe today, but probably not. Okay. All right, and so the other things that I wanted to remind us of, and those of you who hopefully you're at least looking at the homework, if you're not working through all the details, is again, we should think about the normal modes as the wave function of the particle. So if I create one particle, in this case one photon, then if I've created in this mode, this is the wave function of the photon, okay? Or this is the single particle state, okay? So what is the nature of that if we had thought about it from particle mechanics? These wave functions are plane waves in free space. They're vector plane waves, but the fact that they're plane waves means that the particle has a well-defined, in this case photon, momentum. Because these are the momentum eigenstates we know from Schrödinger's equation, right? Yes?
In your lecture 11 notes, there is an I in the front.
Yeah, oh dear. Okay. Oh Lord. This has to do with whether you're quantizing the vector potential or you're quantizing the electric field. In the notes, I did it in terms of the vector potential. Remember that, and often we do, the electric field is equal to the time derivative of the vector potential, right? So if I wrote the modes for the vector potential rather than for the field, then this would be, the electric field would be, for a given mode, is I omega over C times this times. And so then the E's are related to the I's, the E's are related to the A's with an I. So in some ancient notes, I went through this very rigorously in terms of the vector potential. It's another story. I don't want to go down that rabbit hole. Let's talk about that offline. Do this. Learn this. Think about this. Okay? All right. So the point I was making here is that the particles are well-defined. They have well-defined momentum, and that momentum for each photon, if it's created in this mode, is h bar k. Okay? So the momentum operator, not to be confused with the quadrature, which is a different x and p, totally different one. This is a property of the collection of the particles. The other one's a property of the oscillation of the waves. We'll talk about particles and waves. But the momentum in the field is the sum over all the modes, h bar k, times the number. So this is the momentum operator telling me how much momentum there is in the field. Every particle has this momentum, okay? If I have n particles in that field, I have n times h bar k, okay? So, in addition, the Hamiltonian, and this, comes back to Tristan's question about commutation relations, and waving my hand saying, don't worry, be happy. That, as we know from classical electrodynamics and the conservation of momentum, this is the momentum density in the electromagnetic field, and when you plug this all in and you did your homework, you found this, which is beautiful. Oh, I love it. And the energy density in the field is E squared plus B squared. Which is that. So that's the Hamiltonian as we expect. And that's where this characteristic scale of the field is. The strength of the field, whether it's the electromagnetic field, is the square root of the energy density. And the energy density per mode is h bar omega divided by the volume. That's the amount of energy per photon in that mode. Okay. And so this is and moreover, the vector nature, the fact that this thing has a vector, this is really saying something about the spin of the photon. The photon itself is a vector quantity, unlike the phonons that were scalars that we talked about, which is a scalar field. This is a vector field that has three components. Since it has three components, its spin is 1, because a spin 1 has three possible components. However, it's messy and complicated because the photon is massless, that it doesn't have all allowed projections along an arbitrary axis. There are only eigenstates of its projection along its direction of propagation. So we can only talk about its helicity. Its helicity is the projection of the spin along the direction of propagation. And there are only two possible values, +1 and -1, because it's a transverse field. And the transverseness is related to the masslessness. There's a whole bunch of other story in that. So even though it's a spin 1 particle, it only has 2 polarization states. So often we encode a qubit in the polarization of a photon, even though it's a spin 1 particle and has 1 unit of h bar. So the spin angular momentum along this direction is plus h bar for the positive helicity photons and minus h bar for the negative helicity. Yes, Leroy.
I was just gonna say, aren't all bosons like massless? So is
Uh,
that true for all?
I don't think so. I mean, I could have.
I thought it was like force carrying particles.
Yeah, no, I could have. I mean, it depends if I'm talking about the fundamental fields or you know, I can have. I mean, a phonon has an effective mass. It doesn't travel at the speed of light. They're quasi-particles. So, and I could have. Yeah, gosh. I don't know about the W bosons and all those things. I'm just gonna go, I don't know.
So how you measure the third one?
It doesn't exist. It doesn't exist. There is no. That would correspond to the polarization being along the direction of propagation, and it doesn't exist. All right. So this is the quantized electromagnetic. This is the operator. This is written here in the Heisenberg picture because the operators are functions of time. And this is the evolution in free space. Okay? Yeah.
Should one of those be your information conjugate?
It should. Thank you. Very important. All right. Very good. So, all right, this is all very interesting, abstract. I mean, we have the field, we can have particles, we have particles that have definite momentum and definite spin angular momentum. We can have, but what is the heck does this have to do with anything that we understand from classical electrodynamics of what the electromagnetic field is? In fact, it's interesting, I said, a little story. I mean, this was something that just drove me nuts. When I was a first-year graduate student, I had to do a final project for my E&M class. It was a 2-semester course, and I chose as my topic the classical limit of quantum electrodynamics, because I had no idea what the hell did the photon have to do with an electromagnetic wave. And I discovered this set of notes was written by this guy named Roy Glauber in 1964. Or something like that, which was like the pearly gates opened up, and I couldn't believe it. It was the most beautifully written thing I've ever heard. Roy Glauber, who invented quantum optics, and you'll get to read it too, and he eventually won the Nobel Prize, basically for those notes. Well, he did more than that, but Roy was a great hero of mine, sadly passed away a few years ago. Okay. But with that said, so let's just think about, suppose, I mean, what we might want to ask is, if I have some state of the Hilbert space associated with the field. So let's suppose I have a state which has some number, I'll just label these, you know, so there's, you know, K1, V1, 2, mu2, dot. I have some number of photons in each mode, okay? I have many modes. And I ask now, how does the mean electric field vary as a function of time? Okay, so this is the state in the Heisenberg picture. This is the state at all times. And I just look at the expectation. This is, tells me, well, how does the mean electric field vary as a function of time? What's the answer? If I plug that in, how would I do it? Well, I mean, this is going to be this for the positive frequency component and for the negative frequency component. So let's look at this guy, which is going to be every one of these modes. I take the, it's only this, that expectation will pick up one of the modes, and this will be the sum over the characteristic energies, I mean electric fields. Right? Everyone see that? If I take the expectation value, I'm just going to pick off the expectation value of that one thing. Yes?
Does the x not get sandwiched too in the exponential?
X is a parameter.
Okay.
X, the position that we're observing the field at space-time points are not operators. They are classical parameters. Remember, poor old space got demoted. Time was a parameter in non-relativistic harmonics. In quantum field theory, we're not quantizing space-time. We're not doing quantum gravity. Okay? So this is the value at a particular point in space and time, which is a classical parameter. What's the answer? 0. Right? And that's true for the complex conjugate. Same for the magnetic field. So this sure ain't anything like what we would say is a classical field associated with something oscillating at some frequency omega should oscillate as a function of time, and this, the mean, the expected value of the electric field, the mean value, if I were to measure it over and over again, it would be 0. I might get fluctuations. I'm not saying it's always 0. There can be fluctuations around the mean, but the expected value is 0. Yeah?
Isn't that just what we expect for a wave that oscillates about 0 though? Like
No, at every time, you know, if I were to average over time, yes, but this is at a fixed time. But that is an excellent question, an excellent point. This is not the time average. This is at some time. I'm asking what is the electric field, or to measure it. I would get a random value, but on average I'd get 0. Okay? Well, this is similar. I mean, remember, this is a generalization. This is a multi-mode harmonic oscillator. If I had x as a function of time for a single mode, and I ask what is x as a function of time, well, that's x at 0, which we call x cos omega t plus p sine omega t, right, for a single mode. If I thought about what the x is, which is like the electric field, and its conjugate is magnetic field. So if I had a Fock state, an energy eigenstate with n quanta in the mode, what is the mean value of x as a function of time? 0. I mean, no matter what the state is, for a harmonic oscillator, this is true, but this, for a Fock state, zero. So, and we kind of understand that if we thought about this from the point of view as on phase space. If I have a number state, I'm somewhere, I have a definite energy, but I don't know where I am on this circle. I'm everywhere on this circle, which means my mean x is 0 and my mean p is 0 for all the energy eigenstates that are kind of, to some degree, concentrated on these rings that have a certain amplitude, because the energy, a number state, is something with a definite amplitude. I don't know what x is. X is uncertain to some degree, okay? And moreover, the mean x and the mean p are 0. Yes?
Because going back to Tristan's point about how the the electric field operator and the magnetic field operator don't commute, could you do Heisenberg uncertainty?
There, absolutely. In fact, the canonical conjugate to E is A. So E and A, not the chemical, the vector potential. Times some vector stuff. So E is canonically conjugate to A, if I were to actually quantize it.
What's the canonical conjugate?
Well, B is the curl thing. So if I want to write B, then I'd have to write the curl of this. But it would have other vector stuff. But if you quantize in terms of A, the canonically conjugate from Lagrangian is E. But you can vaguely think as E and B like X and P. There's curls and details. There's stuff to talk about. Yeah. Okay, but let's return to this point here. So the state of the field that has a definite number of quanta is nothing like what we would say a regularly oscillating. It has a definite energy, has a definite quanta, but the electric field is not oscillating in any way like a classical field. Yes, Omar?
What if we take superposition of...
Exactly. So let's go back to this. Remember how we got the quantized field? The way we got the quantized field is we had a classical field and replaced the normal mode amplitudes by operators. Let's just go backwards. Let's take the hats off. I wasn't wearing them, so otherwise I would. If I had a state such that let's say the positive frequency component acting on what I'm going to call a quasi-classical state. Got replaced by the eigenvalue being the classical field, that would do the job. Because the expectation value of the electric field operator would be the classical field. The expected value of the operator would be the classical field. So we want to look for states like this to understand what we call something that looks like classical light. What we see in the world that we call the classical field are the states of the quantum field that have this property. So what has out that property? Well, suppose there was a state for a given mode that was an eigenstate of the annihilation operator. Remember, the way we quantize things is we took the classical complex amplitude and we put a hat on it. Here I'm effectively taking the hat off by looking for states that are eigenstates of the annihilation operator. Yes, Donald?
Should there be no plus?
I know I meant the plus, so this should be E plus.
Okay.
Yeah, thank you. I'll come back to the subtleties of E plus versus E minus in a minute. Okay. So if I had a state of the field, which instead of having a definite number of photons, but instead was a state that looked like this, had a different eigenvalue for each mode, this is what I'm calling the quasi-classical state. Actually, let's give it a better name.
Coherent state.
This is what's called a coherent state. The coherent state and a quasi-classical state are the same thing. If I have a state like that, when I apply the positive frequency component to it, what do I get? Well, every time the annihilation operator acts on the state, it gets replaced by its eigenvalue. And so this would then be the sum over all the modes which is the classical field. Yes?
What is making this state the coherent state?
I'm sorry, could you repeat the question?
Like, physically, you call this the coherent state.
Yeah, we're gonna, that's what this lecture's about.
Yeah, right.
So hold your horses.
All right.
I'm gonna explain all of it,
All right. Okay.
either today or this week. Okay? So we're seeking these states. They're called coherent states for a historic reason. It's better for the moment to call them the quasi-classical states. But the states are defined such that every mode, the state of that mode is an eigenstate of the annihilation operator. That's its definition. So let's back up. Let's think about one mode. Let's think about a single mode. Forget about this multi-modes. You know, the modes are transverse waveform. Let's just think about the simple harmonic oscillator. You guys learned this in quantum mechanics?
The simple harmonic, yeah.
No, a coherent state.
No.
But, yeah, this is, Schrödinger did this not long ago, okay? So, all right, so let's consider a single mode. Has some frequency omega. There's a X and a P and an A. We've taken away all the units, okay? The first question, let's look at what is, so firstly, we have a coherent state, which is defined to be an eigenstate of the annihilation operator. Firstly, who's to even say that such states exist? A is not a Hermitian operator. We know Hermitian operators all can be diagonalized. They have eigenvectors and eigenvalues. But we're not in any way guaranteed that a non-Hermitian operator will have them. We'll come back to show indeed that they exist and what their form is. But for the moment, let's just assume that they exist and see what their properties are. Uh-huh.
Can you have an infinite coherent state?
What do you mean infinite?
Infinite number of, it's comprised of infinite number of basis states?
Well, every state, and we'll come back to this, every state in the Hilbert space is a superposition of the basis states. So I want to be careful, Nate, because there's so many notions of infinite here. Every one of the modes lives in an infinite dimensional Hilbert space, right? And can go from 0 to infinity. And this state will find those coefficients soon. But the state is not a number state. It's not an energy eigenstate, and thus it is a superposition. What that superposition is, we'll find that soon. There's another sense of infinite, which is infinite number of modes, right? I said, you know, my state here has a coherent state in every mode. I could have the vacuum in some of the modes and a coherent state in others. Here I'm just talking about one mode. Is that clarified? Yeah. All right, so let's define the coherent state this way. First question is, what is the mean value of the annihilation operator for this state? It's alpha, right? Because if I just put this on here, that becomes 1, okay? So the mean value is alpha. And what is the mean? So if I ask in the Heisenberg picture, how does for a free field, single mode, where the Hamiltonian is h bar omega a dagger a, how does the annihilation operator evolve as a function of time? Right? So that's the time evolution. The solution to the Heisenberg equations of motion is this. We showed this before. dA dt, according to the Heisenberg equation of motion, is minus I omega A. And it's just like the classical equation. But for the coherent state, the mean A as a function of time is what?
Well, alpha of t is the
Alpha times e to the minus I omega t. Just like we expect classically. So the mean value is undergoing a trajectory in phase space, just like we had, or I can think about it as phasor space, or phase space. If I put the square roots of 2, this is x and p, and this goes around like e to the minus I omega t. So the mean value is that. What is the mean x doing as a function of time if I'm in a coherent state? Well, remember, x of t is a of t plus a dagger of t over root 2, right? Yes?
Seeing as x and p are just the in phase and the quadrature parts of A, wouldn't it just be doing the same thing but in...
Exactly. So, but we can also see it formally by taking the expectation of this object. The expected value of this is the mean value of A of t plus the mean value of a dagger of t over root 2, which is
alpha e to the minus I.
square root of the real part of that expectation value, which is the real part of that. So it's exactly, we've effectively taken the hats back off. We put the hats on to get A's and A daggers, but when we're in a coherent state, when we take the expectation values, we take the hats off. Hats off to you. So that's x of t, and the mean p of t is the square root of 2 times the imaginary part of So, for a coherent state, the mean x and p are oscillating in time exactly like the classical oscillator did. But there's more that makes this state special. These states are not eigenstates of position and momentum, right? Because they're not x eigenstates or p eigenstates, they're eigenstates of A. And A doesn't commute with x. So they're not eigenstates of position or momentum. That means that though the mean value follows the classical trajectory, there are fluctuations around the mean, quantum fluctuations around the mean. So now I ask you, what are the fluctuations in position as a function of time? How would you calculate, say, the variance in x as a function of time? It's the variance. How do you calculate that in quantum mechanics?
Expectation squared minus.
Right. And I'm going to do it in the Heisenberg picture because it's easy. Because we have the Heisenberg picture. Okay. So that's the variance written in the Heisenberg picture. Okay. And we just had x of t over there. So this is equal to, so this we just said, right? So this is alpha plus alpha star, alpha e to the minus I omega t plus alpha star e to the plus I omega t over root 2 squared. Okay, yes?
A was complex amplitude. A dagger was modulus squared, essentially.
Correct.
You symmetrize it.
Correct.
Okay.
So, I mean, we really should have a dagger a plus a dagger over 2, but then we did the computation and then we got rid of the 0-point energy. Good. All right, so we got to calculate this. This is equal to a squared at t plus a dagger squared at t plus a dagger at t a plus a at t a dagger all over 2. Right? That's the square of x. And this is a squared e to the minus 2I omega t plus a dagger squared e to the plus 2I omega t plus a dagger a plus a dagger. Everyone with me? Okay, now, since this is true, we have the bra version of it. Right? If I take the bra, I get the ket. And everything becomes dagger. So, whenever you're dealing with expectation values of coherent states, you want to put all the A's on the right and all the A daggers on the left. Because when the A's hit the alphas, you get alpha. And when the A daggers hit the bras, you get alpha stars. That's called commuting into normal order. Okay, the normal order of these, because the A's and A daggers are in some weird order, the normal order, for reasons that are historic, is get the A daggers on the left and all the A's on the right. So, how do I do that? This is a normal order, because there's only A's, it doesn't matter, there's nothing to order. This is already a normal order. Is this a normal order? Yes, because the A's on the right, the A daggers on the left. What about this one? No. So what do I do? You commute it.
Yeah.
So I put it in the other order and I add the commutator, which is 1. Okay? So this thing is equal to a half alpha squared e to the minus 2 I omega plus alpha star squared e to the plus I 2 omega plus 2 alpha alpha star plus a half. Right? Which this is the same as that. Right? So that part cancels. And you get that this is then equal to a half. At all times. Yes?
Just clarifying, because I can't fully see the board, are there no I's in?
This guy has no either, right, because they had the IA, the A and A dagger, and one had either plus I, one had either the minus I. They canceled. Yeah.
Is this an expression of the Heisenberg uncertainty?
Yeah, so, okay, so first thing to notice, interestingly, about this fluctuation, this variance, it's the same at all times. It's a half at all times. And if you do the same algebra for the P, you'll find that this is also true for the variance in the momentum. For a coherent state, at all times, it's that. Which means that at all times, the product, so delta x equals delta p, is 1 over the square root of a half in our dimensionless units. And the product is the minimum uncertainty product. So for a coherent state, we have minimum uncertainty product and equal uncertainty in dimensionless units at all times. So let's draw the picture again. Here's phasor space or phase space, one and the same. Up to factors of square root of 2 in how we're calling the real and imaginary parts. What's going on in phase space? What's going on in phase space is, well, you know, the mean went around in a circle just like the classical oscillator did. However, at any time, I can't say I'm at a point in phase space. I don't know, I can't say when I measure it, I'm gonna get this x and this p. There's gonna be fluctuations around that. And if I just were to draw that, and no matter what time I'm at, so we're here, my uncertainty is the same, no matter where I am. Which means that there is a symmetric uncertainty bubble around this point. The phasor could be a little longer, could be a little high. I don't know exactly what it is. The x and p are not exactly. There's an uncertainty bubble, that's the technical term. Around this point in phase space. But interestingly, for the coherent state, it's symmetric. It doesn't matter where I am in phase space, I have the same uncertainty bubble. So that as this thing goes around, if I were to look at what the uncertainty, just looking at the 1 sigma of RMS, I have 1 over root 2 fluctuations around the mean, no matter what, okay? And they become negligible compared to the mean in the macroscopic limit, okay? So if I were to ask, if I were to try to measure the electric field, or not the electric field, the position of the oscillator, which I can think about for a multimode thing, the electric field, as a function of time, well, that's what it would be, the mean value, but it's really has some noise, quantum noise. Around it. So if I were to measure it at any time, I wouldn't get this white thing. I would get, when I'm drawing in whatever color this is, reddish. And you know, there's some, you know, uncertainty around that. The variance, how much it spreads, is what this Coherent is. And the amount of noise I have at any point in the oscillation is the same.
So, I know, like, whenever you look at, like, when you got, it's like if you take, like if you measure more and more times, it's supposed to get thinner and thinner, but in this case, you say that it has a width.
It does. I mean, if I were to average over time, I can beat down the shot noise. We'll come back to the notion of shot noise. But for a given time interval, there's a certain amount of noise.
So it's called beating down the shot noise?
Yeah. All right. All right. So interesting. So so the coherent state is quasi-classical in the sense that it is oscillating as a function of time, just like the classical oscillator does, but there's uncertainty, okay? If I were to ask, what is the wave function, that's a different story, we'll maybe come back to this, associated with the state as a function of time. Remember, you know, what I will find in this case is that I have something that looks like a Gaussian that is, whose center is moving according to classical trajectory. So what, if I thought about this from the point of view of a harmonic oscillator, what this is a Gaussian wave packet that's oscillating back and forth. That wave packet is not an eigenstate of energy. It wouldn't move. Its center moves according to classical, and moreover, its width is preserved. Okay, we'll come back to how you derive this in a moment. Good. Okay, so we've learned a few things about the coherent state. Its mean quadratures follow exactly the classical trajectory. It's a minimum uncertainty product, and moreover has the same fluctuations at every time, the same variance in time. From a particle perspective, I should think about it as a wave packet oscillating in the well. Now, I come back to somebody's point, I forgot who, that about, you know, being infinite. The question is, this thing is not an energy eigenstate. It doesn't have a definite number of quanta of excitation. What is the mean number Firstly, what is the number operator as a function of time in the Heisenberg picture for the 3 oscillator? It's constant. No matter, it's always the same. And what is thus the mean number of excitations in the oscillator as a function of time?
Alpha squared, the amplitude squared.
Oh, the same thing. It is alpha star alpha. We took the hats off.
Yeah.
We're back to where we were. So the mean number of photons in that mode, if it had a single mode, would be the square of the amplitude. It's the mean number, okay? But the state is not an energy eigenstate. It's not a number eigenstate, so it doesn't have a definite number of photons. It has an uncertain number of photons, an uncertain number of quanta. What is the fluctuation in photon number in this case? Well, that's the mean of n squared minus the mean of n squared, right? Which is that. So how would I calculate this? I put in n and n dagger. So this guy is n times n. Now what? Commutators commute into normal order. So I'm going to replace this by a dagger a plus 1, which gives me a dagger squared a squared plus, in this case, a dagger a. Right? And this is what? Alpha squared, alpha star squared, which is alpha to the 4th. And what's this? Alpha. So, what we have learned from this little exercise is that if I have a coherent state, I don't have a definite number of photons, I have an uncertain number of photons, and the fluctuation in the photon number is equal to alpha squared, which is the mean photon number. Which is to say that the fluctuation in the number of photons in this mode, if I have a coherent state, is the square root of the mean number of photons, which is characteristic of a Poisson distribution. I'm going to come back to that in just right now.
Is that what photon shot mode is?
Indeed. So, this is associated with what we sometimes call counting statistics. Notice that the ratio of the mean number of photons to the fluctuation goes like 1 over the square root of n, which goes to 0 as n goes to infinity. So again, the classical limit really is the limit where the mean number of photons goes to infinity. When I have a large signal, the fluctuations are negligible compared to the mean, okay? That we don't worry about the fluctuations when they're a tiny, tiny fraction of 10 to the 6 photons or something like that we might have in a macroscopic limit. Alrighty. Let's now return to the question, do these things even exist? To have all these great properties, let's look at the eigenvalue equation. Okay. We want to find a state in Hilbert space that satisfies this. So if it exists, it's some normalizable superposition of the basis states, which we take that. So let's just plug that in here. That says that right? That's what we want to have be true. Just plugging that into this equation. Okay.
No. You just put the alpha right there. It's like the square root.
I just plug this into here.
To the right.
In
That's
our
not
final states, just
I just plug this in. I'm not saying I just move the A inside the sum and the alpha inside the sum. And now I seek these coefficients that satisfy this.
Okay.
Now this is equal to what?
Square root of n.
Square root of n times n minus 1. Okay? So this means, hold on, Omar. This means if I change the sum, that this goes from n equals 1, n plus 1, the square root of n plus 1, or, no, sorry. This is equal to the sum n equals 1 to infinity cn square root of n minus 1. Yes, Omar?
Shouldn't the average of n over fluctuation of n be flipped?
I'm sorry, can you repeat the question?
The expectation value of n divided by fluctuation of n.
Yeah.
Shouldn't it be flipped?
Yes, sorry. I meant it the other way around. The fluctuations divided by the mean.
So the fluctuations
Go to 0. I'm sorry, yes, thank you for that. Okay, let's go back to this equation. So the n equals 0 term annihilated and have n equals 1. But I can restart this at n equals 0 by just relabeling things like that. Okay? So when I equate these two, what it tells me is that this coefficient equals that coefficient. So I get a recursion relation, which says Cn plus 1 is equal to alpha divided by the square root of n plus 1 Cn. Okay? So that tells me that C1 must be related to C0 like that. C2 is equal to alpha divided by the square root of 2 times C1, or alpha squared over root 2 C0. C3 ultimately will be this times the square root of 3 times the square root of 2 C0 when you do that recursion. Dot, 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 Cn is equal to alpha to the n over the square root of n factorial C0. So there is indeed a solution. And so what we find is that the coherent state is a superposition of the Fock states that looks like that. Okay? And we just need to decide what C0 is. How are we going to pick that? Well, one way to pick it is by firstly just normalizing the state. Okay? So if I look at the norm squared of the coherent state, that's the sum of the squares of the amplitudes. C0 can come outside the sum. And I get that. Okay? What is the sum? E to the thing. Yeah. So this is equal to e to the alpha squared. That's the Taylor expansion for that exponent. And this, we want, this whole thing, we want to equal 1. Which means the square of C0 squared is e to the minus alpha squared. And we just choose the phase convention. We can't, there's nothing in quantum mechanics that sets the phase. We set it the way we like for this to be real. And so, I'm going to write something down which you must memorize if you're going to pass quantum optics, which is how do I express a coherent state as a superposition of Fock states? Alpha is equal to the sum over all the Fock states, e to the minus alpha squared over 2, alpha to the n divided by n factorial. So that's a coherent state is not a Fock state. It doesn't have a definite number of quanta. If we're talking about the motive field, it has an uncertain number of photons. Okay? If I were to do a measurement of the number of photons in the field, what is the probability if I prepared the field in a coherent state of seeing n photons or n quanta? How do you calculate, generally speaking, without knowing the answer, given a state, what's the probability of there being n, given this expansion? It's the square of the amplitude, right? That's what quantum mechanics tells us, right? If you are superposed in some basis, the probability of finding that is the square of the amplitude, which in this case is the square of this, which is e to the minus alpha squared to the n over n factorial, right? But alpha squared is the mean number of photons, the mean number of quanta. So this probability distribution is e to the minus average n to the n over n factorial, right? Which is called a Poisson distribution.
So,
Yes.
what you're saying that if you got like the same frequency, and you wanna, what it actually means is that the photons are like they are all distributed in that way, like the modes of the photons, they are all distributed that way.
There's very many different things to get confused about. We're talking about one mode. It's not multiple modes.
But the
I'm
sum
saying,
of-
so let's suppose, for concreteness, let's say I have a cavity. And that cavity has some mode which is lasing. Okay? It's got the thing, whatever the cavity, it's got some mode, right? It's lasing at some frequency. It has some amplitude. And I were able to then go in and say how many photons are there in that mode. I wouldn't get the same answer every time. If I had a photon detector and I counted the photons, I wouldn't get the same answer every time. And if I took a histogram of them, I would find they would be distributed according to a Poisson distribution. On average, there's a certain number of photons, and that average is given by the square of the amplitude in dimensionless units. But there will be fluctuations, and those fluctuations will be the square root of n. And if I made a histogram, I would find a distribution. This is about one mode. It's not about lots of modes. And this is not about how the electric field is varying as a function of time. That was about the quadratures. This is about how much energy there is. How many energy packets? A photon is an energy quantum. Yes?
So even though we're expressing this coherent state in the basis of Fock states
Yes.
here, if we operate with the annihilation operator on this coherent state, which by extension operate on these basis states, it still doesn't tell us anything about how, or doesn't do anything to the number
It
of the
does.
state.
Well, it does. Each one shifts down, but the superposition is such, because of this recursion relation, that it comes out that it just gives me a constant out front. So when I operate on this, I get the whole thing back multiplied by alpha. So every one of these n's goes down to n minus 1 with the square root of n in it, but when you redo the sum, it's the same thing as multiplying the whole thing by alpha.
Just comes up to a
That's what the recursion relation, that's how this worked. Yes?
So you said, I measure the number of photons each time I get a different answer, but when I look on the average, I get a definite answer.
Yeah.
Or
Well, the sample mean will converge to the, to the true mean.
Would that be the same if there are no losses in the cavity?
Yeah.
Would that be the same number of, if I knew the number of photons I started with, but I don't know how to know that?
But you don't know the number of
You
photons.
wouldn't know.
So I could try to make a state
Mm-hmm.
that has a definite number of photons. Good luck with that. That's those, single photon emitters or things that emit exactly 2 photons. That's, there's your thesis. But the thing that comes out of a laser is not a Fock state, it's a coherent state.
Yeah.
The thing that comes off of a microwave horn is a coherent state. The thing that comes off of a current of that's radiating radio waves at 89.1 KANW is a coherent state. It doesn't have a definite number of quanta, it has an uncertain number of quanta.
But it has to be so conserved, though, the number of photons.
What's that?
Does the number of photons have to be conserved then? Does it seem like-
No,
Yeah,
energy is conserved, but but my state is not an energy eigenstate. Yeah.
Right, in these situations, I have a definite frequency.
Yes, we're talking about a single mode. But I can have a particle that is in a well that's oscillating a certain frequency, but doesn't have a definite number of quanta. It's not in an energy eigenstate. If it was in an energy eigenstate, the mean position momentum would not change. It's got to be a wave packet. Yes?
Do we have definite photon emitters?
Yeah, we work on it.
Okay.
I want to maybe conclude with just one thing I'll just show here.
Here's a photons. Spontaneous parametric tone conversion, right? So,
Even there, it's tough. I can have post-selective. Well, there's so much to talk about. We will talk about how we try to get close to something that is a definite number of photons. Like anything else, but let me.
So is something that emits a coherent state like more natural than something that emits a definite photon?
Well, I mean, we'll get to that too. Yes and no. I mean, a coherent state has the word coherent in it. The world is not coherent. I may be being completely incoherent right now. But the light that's being emitted from this beautiful LED or from our friend the sun is not a coherent state. It's not a Fock state either. We'll get to that very soon. Okay, here's what I want to show you. Okay, so here's a little Mathematica notebook I just wrote on the airplane when I was coming in this morning. I can't even see that. Okay. So here's my friend, the Poisson distribution, the probability distribution to have n quanta given some n bar, the mean number, okay? It's either the minus the mean divided that to the end, okay? So let's just get a sense of what this looks like, okay? Let's say my mean number of photons was 3, okay? That's, okay, there's the Poisson distribution. It has some fluctuations. It doesn't have a lot of photons in it, so there's a lot of fluctuations relative to the mean. If I increase the mean number of photons to 10, I see the thing shifting. The mean there is at 10, and there's fluctuation. Also notice it kind of looks more Gaussian. That's a relation of the central limit theorem when n gets really big, okay? But what if I go to smaller? Let's say I have, on average, 1 photon. Well, then I have equal probability to be in the vacuum. This is n equals 0, then 1 and 1 photon. They're equal. They're 30-something%. There's also some probability to have 2 photons or 3 photons or 4 photons, even though the mean number of photons is 1. Okay, but the mean number of photons can be less than 1. Doesn't mean that I have a fraction of a photon. It just means on average, if I looked at the mean of that amplitude, and so let's say it was 0.1. So here is a state which on average has 0.1 photons. It means it's most of the time the vacuum. Every once in a while, about 0.1% of the time, it's got 1 photon. Not exactly, because it always has a little bit of 2 photon. There's some chance, this is not a superposition of the vacuum and 1 alone, it also has 2 photons. If I attenuated the sample such that it had in any time interval almost no photons, but every 10th time I'll see a photon, that's like an average 0.1 photon state. It's a superposition of the vacuum and 1 and 2 and 3 and so on.
Yeah. Let's say, like, are you able to know, like, that you have, I don't know if this sounds right, but if you have 1 photon, like, let's say you make 1 photon and then you put in a cavity, and then you measure how many photons are there. So you're saying there's gonna be some time where you get like 0, even though you know you have 1 photon?
If I had no 1 photon and I did that measurement, I would, every time I re-prepare that, I'd get 1 photon for sure. If I had a perfect detector with perfect quantum efficiency that detected the photon and I prepared a 1 photon state, then it's an eigenstate of the number operator, and when I measured it, I would see 1 photon. And if I re-prepared it, and if I did a quantum non-demolition measurement, one that didn't absorb the photon but measured whether it was there, usually we absorb it, so then I would be like, you know, when you measure an eigenstate, it stays in an eigenstate. I'd measure it again, I'd see 1 photon. I'd measure it again, I'd see 1 photon. I'd measure it again, see 1 photon. That's a 1 photon state. This is not a 1 photon state. This is a coherent state with, on average, 0.1. In fact, I can think about a state which on average has one photon, a coherent state that has on average one photon, but which has Poisson distribution. Sometimes I'm going to see 2 photons. A lot of the times, I'll see 2 photons. And sometimes I'll see 3. And sometimes I'll see nothing. And sometimes I'll see 1. On average, I'll see 1. It has an average number of photons, but it has number fluctuations. We gotta take more questions outside because we're already over 5 minutes and there's a class coming in. So let's continue outside. If we had a quantum evolution